Lab 3 Magnetic Field of a Bar Magnet for Physics 2212. In this lab, the distance dependence of magnetic field due to a small bar magnet was calculated by measuring the on-axis and off-axis magnetic fields using the Biot-Savart law. Then, GlowScript was used to create a computational model of the magnetic field of the bar magnet, and the simulated model was compared to the experimental data. Below, you can see an overview of the results found in this lab. For this lab, fundamental principles applied include the Biot-Savart law, which related the magnetic field produced by an object at an observation point to the convention current I and the distance r between the object and the observation point. The magnetic field for a small section dl is shown for a loop with current I on the line passing through the loop. Far from the loop and through the center of the loop is similar to the magnetic field of a dipole on the dipole axis. This magnetic field is related to the distance and the magnetic dipole moment, which is the product of the object's area and current. The field for a magnetic dipole on the perpendicular axis is 1/2 of the on the axis magnetic field. The magnetic field of a bar magnet is also equivalent to the product of k and the distance r to the n power, where k is a combination of magnetic constants. Finally, this lab uses the equation shown at the bottom of the slide as a general formula for the magnetic field of a magnetic dipole. Here we have a visual model of the magnetic field of the bar magnet. Notice that the magnetic field goes from south to north pole and curls around the south pole. The system is the observation point, or the magnetometer, and the surrounding is the bar magnet. Here we have the procedure for the lab. The primary materials include a bar magnet and a magnetometer. For the lab, a series of procedures were conducted to calibrate the magnetometer chip in the phone and collect data on the magnetic fields at different distances, including on and off the axis. Experimental portion of the lab. Notice a line of regression and the decreasing distance between the magnet and the magnetometer as the magnetic field increases. Also note the off-axis magnetic field measurements. Here are a set of equations used to calculate the results previously shown. Using the top equation as a general equation for the line of regression, the k was determined using Euler's constant and exponential function. Using the constants derived from the regression line, the following equation can be set up to solve for the magnetic dipole moment. From these experiments, the two main observations are noted here. The magnetic field increases as the distance between the magnet and the observation point decreases. Additionally, when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. Now we start the computational portion of the lab. Here are the constants for the model as well as the function for calculating the magnetic field. Note that the general formula for the magnetic field of a magnetic dipole is used here. Here's the code for scaling and drawing the arrows of the magnetic field of the bar magnet, which includes the locations of the arrows and what they represent on the axis. Here's the code for calculating the off-axis magnetic field and the corresponding magnetic field arrow. Lastly, here I have the GlowScript model, including the simulated magnetic fields and the resultant magnetic fields. Due to a number of possible errors, such as other sources of magnetic fields, distorting the measurements, including nearby light posts and devices. Additionally, there is possible inconsistency with the placement of the phone, meaning slight movements of the phone during measurements, which could lead to inconsistencies of magnetic field measurements. Another possible error could have been surface inconsistency, meaning that the surface was not completely flat. Lastly, there is possible measurement error when determining the distance between the magnetometer and the magnet. If the magnetic north was not compensated for the measured magnetic fields, they would differ from the magnetic fields with compensation. Both the x and y components of the magnetic field would differ, as the magnetic north would influence both axes, depending on the orientation of the magnetometer. Due to the consistency of the magnetometer being flat on the surface, the z component of the magnetic field should be consistent. If two identical bar magnets were stuck together, the resulting magnetic field would be greater than the magnetic field of one bar magnet. We'd expect this increase in the magnetic field to be twofold due to superposition, though experimental data is needed to confirm this hypothesis. The increased strength of that magnet means that to get the same magnetic field, the distance between the magnet and the observation point would decrease.